Model-based reinforcement learning and robotic task and motion planning have made significant independent progress in recent years. But the assumptions they make are very different. Task and motion planners, which combine symbolic AI with geometric motion planning, assume that necessary planning models are specified, while model-based reinforcement learning seeks to learn models from data. Task and motion planners, however, are able to scale to challenging robotics problems that have long horizons, continuous state spaces, and continuous action spaces, such as these sequential manipulation tasks. In this work, we're interested in how we can learn models like in model-based reinforcement learning that can be applied with task and motion planners to solve challenging robotics problems. Our main contribution is the Neuro-Symbolic Relational Transition Model, or INSERT for short, a class of transition model that has both symbolic and neural components. The symbolic components of an insert are parameters, preconditions, and effects, like those found in AI planning operators. Preconditions and effects are in a language of a given predicate set. The neural components of an insert are an action sampler and a low-level effect model, which together help turn symbolic plans into ground actions that the agent can actually execute in the world. Inserts are relational, meaning that they're not tied to any specific objects. This relational structure is very helpful for data efficiency and generalization. Our planning strategy, based on ideas in task and motion planning, follows a bilevel scheme. In an outer loop, we perform discrete AI planning using the parameters, preconditions, and effects to try to find a sequence of ground inserts that seems to solve the task, at least symbolically. For any such symbolic plan, we then do continuous planning by imagining a state action trajectory using each insert's action sampler and low-level effect model. We then check if the final state in this trajectory achieves the goal. If it does, we're done. Otherwise, we go back to the outer loop and search for a new symbolic plan. Here's an example showing the benefits of bilevel planning. The goal is for the robot to place the red object onto the blue target region. Here, the discrete-only symbolic plan has just one step, which is to put the object down. However, the continuous planning fails to find a collision-free trajectory. So a new symbolic plan is generated that moves the green block away first, which continuous planning is able to turn into a sequence of actions. In this second example only, the only difference is that initially, the green block is in a slightly different place. But this makes a huge difference, as now the action sampler is able to find a valid action for the first symbolic plan, and so the bilevel planning succeeds on the first iteration. In the paper, we discuss how to learn all the components of inserts, which involve techniques from symbolic learning for the preconditions and effects, and neural network regression for the action sampler and low-level effect model. We show in our experiments across robotic planning domains in PyBullet and AI2Thor that inserts can be learned after only tens or hundreds of training episodes, and then used for fast planning in new tasks that require up to 60 actions to reach the goal, and involve many more objects than were seen during training. The remainder of this video shows the results of planning in two of our domains. First, we have the blocks domain. The goal is for the robot to build a particular tower of the blocks. On the left, we're showing the imagined rollout that the agent has in its head when it finds a successful plan, and on the right, we show the result of executing this plan in the actual environment. The two videos look very similar, which shows that the learned models the agent is planning with are extremely accurate. Second, we have the painting domain. The goal here is for the robot to wash, dry, paint, and place some objects into the shelf, and one into the box. The box lid is initially closed, which the symbolic planner does not know about. So the first symbolic plan that the robot tries to refine is one where it can place an object into the box without having to open the lid first. When trying to imagine a rollout of this plan, the neural components of the insert recognize that this is not possible because the lid gets in the way, as you can see here where the purple object cannot be placed into the box. And so refinement of the symbolic plan fails. The next symbolic plan involves opening the box lid first, as you saw us just do there at the start, for which the robot is able to imagine a rollout that achieves the goal. Thus, planning succeeds, And we can see here again that the imagined rollout is very similar to the execution of the plan in the actual environment, showing that the learned neural components are highly accurate. Thanks for watching.